Okay, welcome, calculus friends, to our last section of Chapter 6, Logistic Growth. We are going to reintroduce our friend partial fraction decomposition that we learned last year, and I'm gonna show you why we learned it last year, and its comparison to how we use it for integrals. And then we're going to look at a logistic population model in the terms of calculus and how we're going to do it. So we're going to need all of this stuff to go together at once here. Okay, so let's refresh our memory on partial fraction decomposition. This was actually kind of a fun lesson. I thought it was anyway, last year. This is for if you have a polynomial over a polynomial. Say you had, I don't know, 3x plus 1 over x squared plus 2x. Oh, let's make that a 3x, let's say. Plus a 3x plus 2. And you notice that this has a square in the bottom and a linear in the numerator. Really what we want to be able to do is integrate this ugly thing. Well, we can't really integrate this straight away without using PFD, partial fraction decomposition. So you got to remember, factor the denominator. You need to split that fraction into a sum of two fractions or more fractions if the denominator is a cube or something. And you need to solve for the missing variables. So we're not necessarily going to use this particular example. We might, I don't know if the numbers come out nice. So I'm going to use a textbook example here because I always come out with problems that don't look very nice at the end. So we're going to decompose x minus 13 over 2x squared minus 7x plus 3. I like textbook questions because they usually come out with nice answers. Well, you might remember this. It might take a second to remember this. This is a quadratic of which is factorable, hopefully to 2x. I didn't add that parentheses, but let's go 2x and a 1 and an x and a 3. And since I need negative, both of them actually have to be negative. And that should multiply together to 2x squared minus 7x plus 3. And you might remember this A and this B. Hopefully this is kind of stirring up some memories from last year. And now in order to solve this particular equation, the greatest thing to do is multiply by the common denominator. Well, the common denominator is this 2x squared minus 7x plus 3, or likewise, it's these two factors. So if I multiply the left side, I get x minus 13. If I multiply the right side, this thing cancels, but it cancels and leaves alone an x minus 3. The other one cancels, and it leaves alone a 2x minus 1. And here we go. We go, okay, well, this is just x minus 13. I can't use this for anything. So this is an ax minus 3a and a... actually, this isn't necessarily how it's always done. I'm going to try to show you the trick for this one. Let's go back a ways here. The trick for this is, I didn't really mention this last year, but the trick for this is say, okay, let's say x is 3. When x is 3, it cancels out my a. So if I let x equal 3 here, 3 minus 13 is negative 10. I get a times 0 plus b times, 6 minus 1, 5. So that means that 5b equals negative 10, and therefore b is negative 2. Of course, this is a very fast way to do this. And we could then say, okay, for the other version, let's say x is 1/2. So 1/2 minus 13 is negative 12.5 equals a times half minus 3 is negative 2.5 plus b times 0. Whatever these things makes 0. That's really what I'm looking at here. Well, that goes away. I can divide by negative 2.5, and I get a equals 5. Well, that's nice because I was hoping the decimals would go away. Which means I can now come up here and get rid of this A, get rid of this B, and write in place A is 5 and B is -2. We can put the minus there if we want. Now, how is this handy in integration? If I was to say, hey, let's integrate x minus 13 over 2x squared minus 7x plus 3 dx, and you're like, how do I do this with substitution? Well, you can't. Okay, how do I do it integration by parts? I don't think you can do that either, actually. Well, you might be able to, but it might take a long time to do it. I'm not even sure off the top of my head if you can do that with by parts. But what we can say is we just decomposed this fraction into, what did we decompose that into? We decomposed that into a 5 over 2x minus 1 or minus a 2 over x minus 3 dx. Well, integration of a difference just means I can integrate like this. Well, that's kind of nice because technically the 2 could come out and the 5 could come out. And then we're taking the integral of 1 over 2x minus 1. Well, if I take the integral of something over something, if you want to think about a u, I guess we might want to do that. If we have here, let's say u is 2x minus 1, and therefore du is 2. Here, u is x minus 3, du is 1. Oh, that's kind of nice. But here, we would have a 5. Oops, du is 2 dx, and this is dx. 5 over 2 times the integral of 2 dx over 2x minus 1. Remember the whole multiply by 2, divide by 2, so we can cancel it out, right? This is no different than what's over here. Minus 2 of 1 over x minus 3 dx. And again, nothing has changed. I haven't changed the problem at all. But the reason I can do this is now I can say it's actually 5 over, let's say this is, by the way, u1 and u2. 5 halves times the integral of 1 over u, or du over u, minus 2 u1 times the integral of 1 over, let's call that du actually, over u2. Oh, I know how to do antiderivatives of that. That's just, here we go, 5 halves times the natural log of u1. Well, u1 is 2x minus 1. And minus 2 times, the natural log of the absolute value of u2. u2 is x minus 3. Remember, we have to use absolute values because these things inside could be negative. We want to make sure that they are not. And there we go. We have integrated this kind of ugly fraction, rational function, and we have decomposed it, and then we have integrated it. Now, one thing that I do have to mention is, because I think you're gonna forget, is if we go back to here, notice how I said this is for denominators whose degree is greater than the numerator. So what if I didn't have that? What if I had, for example, 3x to the 4th plus 1 over x squared minus 1, and I told you to integrate this? Well, I would have to decompose this fraction again. Well, it says decomposition is for denominator greater than numerator. Well, I don't have that, but I can get that, so I need to do, you guys are going to hate me, but you're going to need to do some long division. Plus 0x cubed plus 0x to the 2nd plus 1 don't forget your zeros there. X squared, this goes in here 3x squared times, so I get 3x to the fourth, and I get a minus 3x squared. Subtract, this comes down to nothing. This comes down to negative 3x squared plus 1. Oops, sorry, not negative, positive. And I need to add a 3, so this becomes a 3x squared minus 3. 1 minus negative 3 is a 4. So this integration now becomes the integral of 3x squared plus 3 plus 4 over x squared minus 1 dx. Well, that's nice because 3x squared plus 3, that's super easy to anti-differentiate. But you will have to split 4 over x squared minus 1. You'll have to decompose. Okay? So I'm going to kind of stop there because I need to get to the logistic stuff. This, oops, not D, needs decomposing. And then you can integrate this long, nasty thing. Okay, so these problems here, these decomposition problems, they take a lot of work. So don't fret, just do them. All right, so let's go ahead and look into what else we need to cover. And actually, the namesake for this particular lesson is the logistic equations. Biology people probably remember logistic equations. They're actually growth models. And if you recall off the top of your head, the model looks like this. Logistic equations look like this. There's certain things that go on here. But what we are going to do with them is we're going to basically be modeling starting with a rate and creating the logistic equation using anti-differentiation. So here's what we start with. The rate at which the population changes with respect to time. By the way, that's what that means. dB dt, or dp dt, is the rate at which population changes with respect to time, is equal to k times p times the quantity m minus p, where m is my carrying capacity and p is my population, the current population or whatever population we're dealing with at the time. So here's an example, and there's going to be a couple questions that we can ask from this. So the easy question is, what is the carrying capacity? Oh, well, that's easy. This is kind of almost a nonsensical question, but it's ways that you can piece together the equation. The carrying capacity, 1,000. In this particular problem, I like to take stuff from the textbook. This is a moose problem. So we are talking about moose in Ontario, basically. And here's our our carrying capacity is 1,000. A different question that we could ask is, when is the population growing the fastest? Well, this is already a rate, and if we want to know when is the rate the most, you can technically find the derivative of this and set it equal to 0 and solve. What's actually kind of interesting here is it ends up being half of the carrying capacity. So it's actually growing the fastest when your population is at half of the carrying capacity. So if you were at 500. So those are the kind of the easy questions, and you can verify for this for yourself if you were to take the derivative of this function. So you'd get 0.3p minus 0.0003p squared equals 0, and 0.3p minus 0.0006p equals 0. Oops, that p doesn't exist because I apparently forgot how to take derivatives. This is minus 0. And you subtract 0.3 and divide by 0.06, and you should actually get 500. It's kind of cool. It just ends up being half of the carrying capacity. That's when it is growing the fastest. But here's the hard problem. We want to solve this differential equation with the initial condition p of 0 equals 61. So this is kind of hard. So we have to think about what we did in that last chapter, the last section. dp over dt equals 0.0003p minus 1000 minus p. And we got to figure this out. How are we going to do this? I have a whole page for it. So we have dp dt equals 0.00, how many zeros? 3 zeros. 3t, not t, gosh darn it, p times 1000 minus p. Well, we have to split. All the p's have to come over with the p, and the dt gets to go by itself. I'm going to leave this 0.0003 by itself, though, and I'm going to get, divide by that, I get dp over p times 1000 minus p. Goodness gracious. 1000 minus p equals 0.0003 dt. Well, now what? Well, now we need to integrate both sides. Well, if I'm going to integrate this side, this becomes 1 over p times 1000 minus p dp equals the integral of 0.0003 dt. I'm going to kind of speed through a little bit of this, but I will explain what I'm doing here. This is a rational function, which means the whole point of the first 2 slides where I talked about decomposition, this is where decomposition comes in. So you're going to have to go 1 off the side. You're going to have to do 1 over p times 1000 minus p. Can't get 1000 apparently. Minus p equals minus p equals a over p plus b over 1000 minus p. I cannot write 1000 for some reason. Now, again, because I'm using a textbook version, I'm going to speed this process up a little bit. I end up getting 0.001 over p plus, again, 0.001 over 1000 minus p dp. I'm laughing at myself here. Integral of 0.0003 dt. Okay, so this looks ugly. But here's what you can do. I always try to simplify problems as much as I can. Notice I have a 0.001, 0.001, 0.0003. I can multiply both sides by 1000 to make my problem a little bit easier. And I get the integral of 1 over p plus, or dp. I'm going to split this up now. Plus 1 over 1000 minus p. And again, I cannot write 1000 for some reason. dp equals the integral of 0.3 dt. Oh, okay. Now what? Well, you've probably learned ways to speed this process up a little bit. The integral of 1 over p is the natural log of p. Notice I'm not using absolute values here. You might take a guess as to why, but I'll tell you. P represents population. We shouldn't have any negative population. That doesn't make any sense. Minus, now because you use a u substitution right here, the derivative of 1000 minus p is actually a negative 1, which makes this a minus ln of 1000. Hey, I did it. Minus p equals 0.3t. Well, that one's easy. I like that. Plus c. Ooh, my c missed. Let's write this a little bit smaller. 0.3t plus c. Some of you might forget what we are doing here. We are actually trying to figure out an initial value problem, which means we need to do some stuff here. Okay, so let's say, because we can do this, let's say this is natural log of 1,000 minus p minus the natural log of p, which just changes the sign over here to a negative 0.3t plus c, or minus c, I guess, technically. And your logarithm properties say if I have the difference of two logarithms, I can create it as a quotient. And to get rid of the natural log, I can take e of both sides, and I can say 1,000 minus p over p is equal to e to the negative 0.3t minus c. And if you put the minus c up there, you can actually kind of get rid of something if you really want to. I can put the e to the negative c right here, because multiplication will add exponents, so I'm just going to do it that way. Now I need to find some more room, so I need to do a little bit of erasing over here. So bear with me for a second. Hopefully you wrote all that down. Did I ever tell you that calculus is going to be hard? Good. Or not always easy? Good. I hope I did. Okay, back to the pen. Now we have 1,000 minus p over p is equal to e to the blah, blah, blah. We can actually simplify this fraction a little bit if we wanted to. It's actually 1,000 over p minus 1 equals e to the negative 0.3t times e to the negative c. Add 1 to both sides. And now we can use our initial condition. It took forever to get to this. Our initial condition is p of 0 is equal to 61. So when p is, time is 0, by the way. When time is 0, the population is 61. And if you did all of this, which I know you can all do, it tells you that e to the negative c is equal to about 15.39. Which means I now get 1,000 over p is equal to 1 plus, remember e to the negative c is just this thing out here, 15.39 e to the negative 0.3t. I do a little trickery. I flip both sides and I multiply by 1,000. I finally get the logistic equation that you guys are used to. 1,000 over 1 plus 15.39 e to the negative 0.3 t, and we finally solved that problem. Wow. That's a pain in the butt. But guess what? The more you do these, the more worthwhile they become, because you get a better sense of the calculus behind some of these problems that you've just taken for granted for the last couple years. All right, and again, you see this 1,000 in the numerator. That's our shoot, what do I call it? Our carrying capacity, that sort of idea. All right, I'm going to leave you guys with that. You guys will be needing to do logistic regression, which means you need to plug in some table values into your lists and use logistic regression to create equations. All right, I will see you guys tomorrow. Hope you guys do well on this stuff tomorrow.